All right, guys. So looking at the law of sines, we are going to understand today the derivation of the law of sines using the SOHCAHTOA stuff that we already know. And we're going to be able to solve any triangle given two angles and a side combination, whether it's an angle-side-angle combination or an angle-angle-side combination. We'll be able to do both. We are also going to be able to determine how many triangles are possible when you have a side-side angle, and then solve for the possible triangles. If you guys will remember from geometry, all of this stuff was like proving when triangles could be congruent, right? So we had angle, side, angle, 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 side. We had a few more. What about this one? That spells a bad word, right? So we never used that in geometry because it doesn't guarantee that two triangles are congruent. However, it does give you enough information to solve for possible triangles out of it. Okay? Don't write this down. You can just watch. This is just me kind of getting you ready for the lesson. So the whole point of this lesson is looking at oblique triangles. What is an oblique triangle? An oblique triangle is a non-right triangle. So why do we care about that? So far you guys have just... Shane, stop messing with your neighbors. Okay. Shane, just stop talking to the people around you. And Ian, stop. Or not Ian, I'm sorry, Christian, stop. All right, so as I was saying, why do we care about an oblique triangle? It's because so far you guys have been using SOHCAHTOA, but what is the only case where you're allowed to use SOHCAHTOA? In right triangles. So we need to be able to extend this. The natural next question is, what do we do when we don't have a right triangle? Can I still find all of the missing pieces? And the answer is yes. All right. You guys don't need to draw the pictures. If you want to just write down what the congruencies are so you can remember what they are, that's fine. We have side, angle, side. Remember that the order of the letters in the congruency does matter. This side angle side congruency specifically says when you have two sides and the angles sandwiched in between, and that is important, is that when you're looking at a picture, that would be this case where you have two sides and the angles sandwiched in between. The next congruency we had was angle side angle. That's another sandwich. This time you have two angles and the sandwiched side in between. So that looks like this, the two angles and the side that's right smack dab in the middle of them. Another congruency, probably your easiest, is when you have a side, side, side. So all three sides. Okay, so having reviewed that, the data that's required to solve an oblique triangle are any of these cases. So you might have one side and two angles in either of these forms. You might have two sides and one angle, which is not between the two sides. That's kind of our ambiguous case that we're going to have to look at because that's the bad word one, right? Case 3 is when you have the side angle side sandwich. That one's fine. Case 4 is when you have side, side, side. So we're going to kind of take a look at these all in turn. Today we're going to look at case 1. Also, make a note, why isn't angle, angle, angle enough to solve a triangle? If you know all three angles, why can't you find the sides? Yep.
Because the sides can be anything. Or like, it's similar. You just like make it bigger or smaller.
Yeah, you can take those same angles, and so basically you can have similar triangles with AAA, right? But you don't necessarily know to what scale the sides are to each other. So for an example, an equilateral triangle is always going to have what sides or what angles? 60s all around. So if I gave you a triangle that was 60, 60, 60, do you know what the sides are? You have no idea whether the sides are small or big or what. right? So that's why that's not enough information. All right, let's take a look at case 1. This is given 2 angles in one side. In this case, we don't need it to be a sandwich, and we don't need it to be angle, angle, side, or side, angle. It doesn't matter. We just need 2 angles in one side in any combination. So let's look at what is the law of sines. Where does it come from? So basically what I've drawn here is an acute angle and an obtuse, or an acute triangle and an obtuse triangle. Because if we're assuming that I don't have a right triangle, then it's either this case or this case, right? And we're trying to figure out how could I use SOHCAHTOA to the best of my ability. So notice that I dropped a height from C in both triangles, right? That forces a right triangle, and now I can start using SOHCAHTOA to try and write some relationships. So let's look at these triangles. Let's say, and notice that I'm saying law of sines, so which trig function am I only working with here? Sine. I'm only going to work with sine. So let's say that I wanted to come up with a relationship for the sine of angle A. Take a look at this picture. I have to use the right triangle. So what is the opposite side of A when you're looking at the right triangle? Opposite side of angle A. Is it H or A? H. I have to look at the right triangle. So I have to focus my efforts only on the right. So H over sine is opposite over hypotenuse. H over B, right? Okay? Notice that that means that B times the sine of A is equal to the height. Does that same relationship hold in this triangle? So take a look at angle A. You've got angle A, opposite of angle A is on the right triangle. Come on, guys, work with me here. H over, same thing. So it does not matter whether that is acute or right, or acute or obtuse. Let's do the same thing from, can I use the right, I'm trying to think of how to say this. Can I use angle C with this right triangle here? Does that make sense? Why not? Is the right triangle using all of angle C? No, it is not. So I can only otherwise look at angle B. Does B still have a right triangle? Yeah, it's just this little guy. So let's write the sine of B in that one. So the sine of B is equal to what? Yeah, H, or opposite H over hypotenuse A. So what does H equal in this case? A sine of B, right? Let's check the obtuse triangle. This one's a little bit trickier. If I want to use the right triangle from angle B, can I use the measure of B here? No. But this angle is what? 180 minus B, or we might write it as pi minus B. Now think through what we've been doing with those cofunction problems. Pi minus B, when you're looking at the sine, what is that the same exact thing as? No. That would be if it was pi over 2. I said cofunction, and what I meant was when we were solving the equations using the cofunction method, we said that if we have two sine things that are the same, we said it could either be the angle equal to itself plus 2 pi k revolution, or it could be equal to the angle pi minus the angle, because are those two things the same? So what is this the same as? The sine of B, right? What that whole thing we did before was saying was that sine of an angle is equal to the sine of pi minus that same angle. So in the obtuse triangle, if I were to be writing this, I'm focusing my efforts right now on this angle right here, yeah? Which was the pi minus b. What is the sine of this angle right here? Opposite is h over, right? So this thing that we get from the obtuse triangle, is it exactly the same thing that we got from the acute? I think so. Right? Same thing? So no matter which triangle I get, I have the relationship that h could equal this stuff or h could equal this stuff, which means that b times the sine of a should be able to be equal to a times the sine of b. Agreed? Okay, well what can I do here? I could divide out by this b and divide it onto the other side, right? So I could say, put this over b. Couldn't I do the same thing with the a as well? Yeah, so I could get the a off of this side and divide it over here. So I get these nice ratios. The question is, can I put the sine of c over c as well? Does that follow? I am going to really quickly erase all of this stuff. You guys can keep it on your paper. I'm just trying to give myself some space. Notice that I just drew the altitude on the triangles here. I just picked one of the vertices to draw down from, right? Did I have to choose to draw from C? Couldn't I have also drawn from B? If I drew from B, would all of this work follow, except for which angle would I be discluding this time? Rather than discluding C, I would be discluding, but all of the work would be exactly the same, and I would get that the sine of A over A was equal to the sine of C over C. All of that work, again, would be exactly the same since it's the same whole scenario except for I'm drawing my altitude from B instead of C. Now that I know this, can I link all of these together? Yes. So the law of sines says that, and I'm going to put it all together here, says that the sine of A over A could equal the sine of B over B could equal the sine of C over C. Notice that I wrote the angles on top. Could I also write this as A over the sine of A equals B over the sine of B equals C over the sine of C? Yeah. What you guys want to do is look at where are you missing a piece of information. So if I'm missing an angle, I would probably want to use these forms so that I'm keeping my unknown on top. If I'm missing a side, I'll probably use this form so that my unknown is on top here. Notice that this is just saying that if you take a ratio of a side to the sine of its opposite angle, any of those ratios will be the same, right? So let's see how we can make use of this. All right. So here we're given a triangle. I don't really have to draw it because can you guys already tell which sides and angles are opposite of each other based on the labeling? We're assuming always that a capital case letter is directly opposite of the matching lowercase letter. We'll always assume that. Okay? So here, we need to solve the triangle, meaning we need to find all angles and all sides, right? What's the easiest thing for me to find? I have two angles and one side. What's the easiest missing piece? The last angle is probably the easiest because all angles in a triangle should add up to 180. So I can find angle B simply by taking 180 minus my 102.6. Keep in mind the capital letters are always going to represent the angles. The lowercase letters are always going to represent the sides opposite to those angles. And then we would subtract 25.3 as well. Can I have some help? What is that?
28.8, not 5.3.
28.8?
Yeah. No.
What?
Replace 25.3 with 28.8.
Oh, I see what you're saying. I'm sorry. I used decide. Is that what you're saying?
Yeah.
I did. After I said all of that stuff. And I used decide. Thank you for catching that. Okay, what does that equal? What?
I got 48.6.
Okay. So we've got 48.6. So now I have all three angles. I'm missing two of my sides, right? I can find any of the sides pretty easily by using the law of sines. So let's say that I want to find side B. I would put little b over what? Sine of 48.6, the sine of angle B. And set that equal to? Am I going to use the A's or the C's? C's because I don't know little a yet, right? That would do me no good. So I'm going to use little c, which is 25.3 over sine of capital C, which is 102.6. So then to solve for little b, all that I have to do is multiply up by that sine of 48.6, right? So it will be b equals 25.3 times the sine of 48.6 divided by the sine of 102.6. The one thing to watch for, you guys, is that your calculator is going to be opening parentheses for the sine here. Make sure you close this parenthesis before hitting your division key. Do not round anything until you have got all of this. What do you guys get? And we'll round it to the nearest hundredth place, but again, don't round mid-problem. All right, so when we punch that in to the nearest hundredth place, we get 19.45. We're going to do a really similar setup to find little a. The only difference is that we're going to have little a over the sine of capital A is 28.8. Does anything else change in my other fraction? Does it? No. Do I want to use this? Why not? It's a rounded value. You should not use that to find something else. These are perfect values, so I should just reuse those. So that means that A is going to equal 25.3. The only thing that changes, so what you guys can do is press that second entry button. So it's like the second button. The entry button is down by the enter somewhere. If you press that a couple of times, it'll take you back to whatever you punched in up here. Whoops. Whatever you punched in up here, and then all you have to do is just kind of change that up. If you don't want to repunch it all in, that's an option, but you don't have to do that. So we're doing 28.8 instead of 48.6 divided by the sine of 102.6. What did you guys get? What? Okay. What is something you can do to check to see if these are reasonable numbers? Your smallest angle should be across from the smallest side, yada yada. So in other words, what's my largest angle? So C should have the biggest side. Does it? Yep, there's C. It's bigger than either of these. Okay, what's your middle angle? B. Does B have the middle value? Yeah. So that's something you can do to check if it seems reasonable to you. Okay? Let's look at another problem. Do you see how much easier that was than what we've been doing? Yay. Okay? Just leave it on my desk, please. Okay. The only thing here is that you have to make sense of what's happening, right? So we have to kind of use what we know about bearings. I'm giving you guys kind of a new notation, well, not new notation, kind of a more specific notation with the bearings, because I am giving you now specifically which directions I want you to measure from. So let me show you what all of this means. This means that you have got a ship, and give me 1 second to get in drawing mode. All right, you've got this ship, and we're saying that if I measured off of the north line due west 52 degrees, I would find where my lighthouse is, because I'm measuring the bearing of a lighthouse from the ship at that kind of degrees, right? So what that means is that if I drew the north line off of the ship, and I measure out 52 degrees in the westward direction. Thank you. I would find the lighthouse up here somewhere. Okay? It says that the ship travels, oh, and I didn't give myself very much space, but the ship sails 5.8 kilometers due south. So that would be the ship doing something like this, and I know I'm making it a teeny tiny little triangle, but I didn't give myself much space. If it travels 5.8 kilometers due south, the new bearing to the lighthouse, so in other words, if I now were to connect the lighthouse to where the ship now is, that new bearing would be how much? What? 23 degrees. Oops, sorry, I didn't see that I went off into the dossier thing. Let me redo that. Can you guys see that? Yeah, okay. So what we need to do is find the distance between the ship and the lighthouse at each location. So in other words, I need to find that distance from the ship to the lighthouse and that distance from the ship to the lighthouse. Can you guys kind of see what's going on here? I know I didn't draw that very big at all. Hopefully we can tell. How am I going to do this? What I'm going to do is kind of draw a better triangle off to the side that represents exactly what's going on here, right? So that I can kind of see where everything is. So I'm just going to kind of make a bigger version of this and, whoa, it's not what I wanted. Make a bigger version of this same thing and kind of better label it so that I can really see what's happening. Okay, so I know that this angle down here is still 23 degrees. I'm looking for X and I'm looking for Y. Notice that here, I need to kind of make sense of what that angle is. Over here with the bearing, I was told that this is 52, so how am I going to figure out what this angle is? 180 minus 52, which is going to give me, what? 128. Can I now find my third angle? How are you going to do that? Subtract them all from 180. So what is 180 minus 128 minus 23? 29. I now have all of my angles and I can use law of sines. This isn't a right triangle, so I can use law of sines though to find X and Y. So what is going to be my setup to find X? And I shouldn't be writing x equals. What? I don't have to draw anything else going on. I can go straight from the picture I've got. Use your law of sines. Remember, law of sines is so that you don't have to find a right triangle, right? That's the whole point. X over the sine of the opposite angle. Yep. So x over the sine of 23 degrees. And what would I set this equal to? You need to use the side that you know, right? So, and I didn't put that in there yet. What was that? 5.8. So I need to use the side that I know, which is 5.8. And what do I have to put 5.8 over? Sine of the angle it's opposite, which is going to be, 29. So now to find x, all that I have to do is multiply, and actually I'm not going to write the whole thing out again. I'm just going to take this 23 off the bottom here, multiply it up here. So what does x equal? To the nearest hundredth we'll do, so we'll do an approximation. 4.67. One thing you guys need to check, and it sounds like all of you have done it, but make sure that your calculator was in degree mode, right? That was something to watch out for, is that you're going to have to kind of be making sure you're in the correct mode. All right, I still have to find y, so what's my setup to find y? Y over, what's opposite y? So the sine of 128 equals, and then I still just use the things that I knew exactly, so I'm still going to use this fraction right here, the 5.8 times the sine of 29. Again, multiply that sine, this time it's sine of 128 up. What do we get? Sorry, what was that? 9.43. Are there any questions on that problem? No? Okay. So the second case was if you were given two sides and one angle, right? Okay, let's first look at, and specifically, and I should say this, specifically we're looking at the case where you have two sides and one angle where it's a oops, hold on. We're specifically looking at right now the case where it's the side-side angle, the one that we didn't like in geometry, and you'll see why we can't use it in geometry for congruent triangles. All right, we call these things the ambiguous case, and you'll see why. So first we're going to look at the ambiguous case when you have an acute angle A down here. Okay, we're assuming that we have the sequence where you're given two sides, so a side and an angle, and we don't know how long that third side is. Nor do we know what this angle up here is, right? I'm kind of drawing this in a sense that you can kind of see what could potentially happen. All right. Ambiguous case number one is if you're given this angle A, so you are forced no matter what to keep this angle. I can't hinge this higher or lower, right? This side is going to have a specific length. So right now, I have this dotted line because I don't know how long this line is, but I know at least that I formed this angle and that B has to reach up to here. And then I'm given a second side A. The question is, can you form a triangle with A if A is shorter than the height of that triangle here? Is it possible, visually, you can kind of see this, is it possible for you to get A to ever reach that third side? No, that's impossible, right? So it's potential in a side-side angle that you're going to get a case where you don't have any triangles. Okay? Are there any questions on that? Right now, we're just looking at visually what could happen, right? Now, let's say that I were to start extending A. What is the next kind of important step of A? Like, what's the next length of A that we would want to consider? We said A is less than H. Now it's the next case. If A is the same as H, right? What happens if A is the same as H is that the only way you can connect that down to the side is on the height itself. So how many triangles are possible here? And specifically, what kind of a triangle will that be? A right triangle. Okay, what's the next case? We've done if A is shorter than the height. We've just done if A is exactly equal to the height. So what is the next case? If it's longer than the height, what does that look like? You have two possible sides in this case, okay? So ambiguous case number 3 is if A is longer than the height and can windshield wiper inside of the triangle. What I mean by that is if this distance A could be, if it's longer, it can either extend out or it can extend in and form a triangle here. I can't remember if I did a slide like that, so let me see. Yeah, so you can see right there. Those are your two potential cases if A is longer than the height, right? Any questions on what's happening with that? A couple more times so you can see it. So the fourth case is when A is longer than B, and so if you were to windshield wiper it, it would windshield wiper too far out here and wouldn't give you that second triangle, in which case you only have one possible triangle. All right. So now we have to look at what happens if angle A is obtuse. Lots of different cases, right? So now if angle A is obtuse, but it still is that same thing where you've got a set angle that you have to measure. You've got a set distance B off of that angle, and then your second side, you're trying to see what has to be true for this in order to get a triangle. Okay? Instead of using the height as our reference length, now we're just going to use B as our reference length. Okay? So if you have an obtuse triangle, and A is shorter than B, is it ever going to form a triangle? No. You will get 0 triangles in that case. All right. So the next distance we want to look at is if A is greater than B. Okay? Why didn't I say if A is equal to B? If A was equal to B, would it form a triangle? No, because it would have just come straight down on B again, right? But if A is bigger than B, then it can extend out and it can form one triangle. All right? So take a look at this scenario and let me know, does a triangle ABC exist? They don't care how much, they just say how many triangles, they just say, does it exist? So the first thing that you want to take a look at is what kind of an angle are you given? Is this acute or obtuse? Obtuse, right? So we actually only had a couple of cases for obtuse. So what you've got right now, and I'm going to kind of draw a sketch to help you, but then you have to verbally explain, is an angle that's 93 degrees, which is going to be just a little bit bigger than 90, right? Something like that. So this is your angle B that's 93 degrees. Your side B, is it possible for this to be your side B? Why not? Little b should always be opposite. So this could be C. Yeah, so this could be little c, which is 48. So now when I'm drawing that side that hinges off here, that's my little b. So the question is, little b is 42, right? Knowing that little b is 42, is it ever going to reach this part of the triangle down here? Why not? Yeah, because little b is 42 is shorter than c. And you can kind of say, and we'll never close the triangle. Any questions on that? Yes.
So can we look and say that B is going to be the largest angle, so therefore side B has to be the longest side, so there's no triangle?
You could say something like that as well. Yep. So Shane just asked us to repeat. He asked, could I say something along the lines of B has to be the largest angle? Why do you know that there can't be an angle bigger than B? Because it's obtuse, right? And you can only have one obtuse triangle, or angle in an obtuse triangle. So both of these other angles would have to be acute. They definitely would have to be smaller than B. And yes, the largest side would have to be across from that. 42 is not the biggest side. So that would also be a good explanation. I'm going to stop here today for this. We'll pick up tomorrow on the rest of that.